All right. Imagine a sphere whose radius is decreasing. Maybe y'all laugh at me, not with me. I don't know. Imagine a sphere whose radius is decreasing. When the diameter of the sphere is 6 feet with respect to the radius, how fast is the volume of the sphere changing? Explain your result. Okay. This kind of has a taste of types of questions we'll be looking at later in the year called related rates. This one's different, though, because we're looking at how fast a shape is changing with respect to another dimension of that same structure. So we have a sphere. Here is a depiction of a sphere. The critical measurement in any sphere is its radius. We have a formula for the volume of a sphere that you need to memorize. Does anyone happen to know what it is off the top of your head? The volume of a sphere. 4/3 pi r cubed. Yeah, 4/3 pi r cubed. So memorize that if you don't have it already memorized. It'll show up quite a bit throughout the year. 4/3 pi r cubed. You can look down if you need it. There it is too. All right. So imagine a sphere whose radius is decreasing. So the radius is getting smaller when the diameter of the sphere is 6. So I call this your snapshot moment. Your snapshot moment. You have a sphere and the radius is decreasing. And you take a picture of it right there when the diameter is 6 feet. So I always draw one of these retro cameras. So when the diameter is 6 feet, that's the same thing as referencing when the radius is what? 3 feet. Good. So it's really the same moment in time. This captures the instantaneous nature of this type of problem. That's why it's calculus. Then at that moment, how fast was the volume of the sphere changing? Well, let's see. The volume is 4/3 pi r cubed. And I want to know how fast... Oh, I forgot pi. That my wife would be proud. But it's not. It doesn't make it right. She's trying to get me to quit eating sweets. 4/3 pi r cubed. There you go. 4/3 pi r cubed. I want to figure out how fast that quantity is changing at an instant. So I need its whatative? Derivative. So let's go ahead and find the derivative. V prime is going to equal 3 times 4/3 pi is 4 pi r squared. Good. 4 pi r squared. Now, in order to compute this, I need to know what the radius is at that moment. Do I know what the radius is at that snapshot moment? Yeah, it was 3. So if we hadn't found it yet, we would know when the diameter is 6, the radius is 3. So now we'll say V prime of 3 equals 4 pi times 3 squared, and we end up with a final answer of 36 pi. Now, what would the units be? Feet cubed, right? Per, it's a rate of change of volume with respect to what? The radius. What do we measure the radius in? Feet. Yeah. So with respect to the radius at this moment, when the radius is 3, the volume is increasing, we could say. The volume is increasing by 36 pi cubic feet per 1 foot. Bless you. And because the radius is decreasing, we could actually say this. Let's write the sentence. It's not a negative number because we know the radius is decreasing, so we know that the volume has to be decreasing too. So when the radius, we'll write it out, is 3 feet, comma, the volume of the sphere is decreasing. And even though it's not negative, we know it's getting smaller, is decreasing by 36 pi cubic feet per foot. Okay? Instead of per time, we say per foot, which means at that moment, if the radius were to get 1 foot smaller, the volume would decrease by another 36 pi cubic foot. Foot. He's here in spirit, is he not? Okay. Surface area. At that same moment in time, we took our picture. We're going back to our math lab. Math lab, not meth lab. We go back to our math lab, and we want to compute now all the possible things at that moment in time that we can. So I want to know how fast the surface area is changing. We know the surface area should be getting what? Bigger or smaller? Smaller. If the radius is getting smaller, everything about it's getting smaller. So what's the formula for the surface area of a sphere? 4 pi r squared. Good. 4 pi r squared, I'm having a little bit of deja vu. Didn't we have 4 pi r squared right here? It turns out the derivative of the three-dimensional representation of a sphere, volume, the derivative of that gives you its two-dimensional measure, the surface area. And it works with circles too, right? What's the area of a circle? Pi r squared. If you take the derivative of it, you get a prime, which is 2 pi r. That's a measure of its circumference. Yeah. So you can take the derivative of those formulas and get the one dimension smaller equivalent formula. So that's pretty cool. So now I want to know how fast that's changing, so I need its whatative? Derivative. Now I'm not going to use a prime notation here. I'm going to use Leibniz notation. So dA dr, instead of a prime of r, is equal to 8 pi r. Now I need to plug in a what? The radius value, which is 3. Now in function notation, we show it like that, v prime of 3. In Leibniz notation, here's how we show it. It's the way your calculator did it in section 2.2. We use the evaluation bar, the when bar, and we put r equals 3 down here. So that means we're about to evaluate that expression when r equals 3, and we plug it in and we get 8 pi times 3, which is 24 pi. And what are the units? It's a rate of change. So this is another reason Leibniz notation is beneficial. Yeah, it's units of A divided by units of R. So it'd be feet squared per foot. Ugh. Now, I didn't talk about this in the last example, but hey, feet squared divided by feet, isn't that just feet? Doesn't that simplify to feet? It does, right? But do you want to do that? You would lose the context of the question, right? You would then say when the radius of the sphere is 3, the surface area of the sphere is decreasing by 24 pi feet. That doesn't make any sense, does it? No. So even though you can divide them out, don't do it. You would say that the surface area is decreasing by 24 pi square feet per foot. Got it? I'm not going to write it because that's just a lot of writing. But you got the idea. How fast is the diameter changing at that point in time? We're back in our math lab, remember? Well, let's see. I need to be able to relate the diameter to the radius somehow. Let's call the diameter big D or little d? Big D? Okay. Big D equals 2r, right? All right, sweet. And I want to know how fast that's a changing, so I need its whatative? Derivative. So let's use Leibniz again. I like it. So dd dr is going to be what? 2. So let's go ahead and plug in now when r equals 3, and you get what? 2. And what are the units? It's units of diameter per units of radius, which are going to be feet per feet. Yeah, which is 1. So you don't want to divide those out, or the units go away altogether. So when the radius of the sphere is 3 feet, comma, the volume is decreasing by 36 pi cubic feet, the surface area is decreasing by 24 pi square feet, and the diameter is decreasing by 2 feet, all per what? Per foot, per feet. Yeah, yeah, feet. All right, so memorize these. The volume of a sphere, V equals 4/3 pi r cubed. The surface area of a sphere, 4 pi r squared. And the shape of a sphere, round. Round. Okay. Here is a summary of some of the things we're about to encounter in the examples that we work. I'm not going to go through all of that because y'all can read it on your own, but I will mention a few of them. The first one we've already seen. That is the relation among the 3 kinematic equations for falling objects on or near the surface of planet Earth, right? Or in general, it doesn't have to be planet Earth. This would relate all of them once you have the equations. The second derivative of position is the first derivative of velocity, which is acceleration. Displacement is net change in position. It's your final position minus your initial position. So if we let S of t be the distance equation, then S of b minus S of a is the displacement on the interval from A to B. Average velocity. Average velocity is going to be the displacement over time. It's the difference quotient. It's the slope of the secant line of the position graph. whereas the instantaneous velocity is the derivative. Speed is not a vector. It's a scalar quantity. So speed is the absolute value of velocity. This is kind of important. You're going to be asked if speed is increasing or decreasing. Speed is increasing when two things work together, namely velocity and acceleration. If velocity and acceleration have the same sign, they're both positive or they're both negative, then something is going to be speeding up, or the speed is going to be increasing. If the velocity and the acceleration are opposite signs, they're working against each other, now the speed is going to be decreasing. And so you have to look at those two things to determine what a scalar quantity like speed is doing. So imagine like you're running in one direction and you have a tailwind, right? You running is velocity, the tailwind is the acceleration. You're going to get a little help from the wind, you're going to go faster, okay? So that would be velocity and acceleration working together. But if you're running into a headwind, now you're the velocity, the acceleration is coming against you, it's going to slow you down a little bit, okay? So that would be if they worked against each other. And the direction doesn't matter as long as they're the same sign. Now, velocity is a vector quantity. So there's a difference between me asking you, does speed increase or does velocity increase? Speed being a scalar, you have to compare acceleration and velocity at that moment. But to determine if the velocity is increasing, all you have to do is look at the acceleration, because that's its rate of change. If the acceleration is positive, velocity is increasing. If acceleration is negative, velocity is decreasing. You don't need to look at two different things. Okay, and something will change direction when the velocity changes signs, whether it's from positive to negative or negative to positive. Okay? Here we go. Example 6. A particle moves along a horizontal line. That's a pretty typical scenario in a lot of these problems. You can think of the x-axis as being a track in which this little particle or bug, you can call it a bug if you want, you can call it a racehorse if you want to trump it up to something that makes you appreciate the problem more. But you got something that's moving in a straight line path, left and right, left and right, left and right. Okay? So that its position along that horizontal track at any time greater than or equal to 0. Keep that in mind when you're given something like this. Negative values of t don't make sense in this problem. We're only looking at positive t's or 0. It's given by this quadratic function. X of t is equal to t squared minus 4t plus 3. So if I plug in any value of t greater than or equal to 0, I will know exactly what the x value or the x position of that particle is on the x-axis, essentially. Where x is measured in feet and t is measured in seconds. So now we know we have units. So that's a unit alert. We're going to have to put units on every one of our final answer. Okay, here goes we. Example A. Find the displacement of the particle during the first 3 seconds. Explain its meaning. So how are we going to figure out the displacement? Displacement is your net change in position. So the displacement, DISP, is going to be your final position. We're going during the first 3 seconds, right? So I want to know where was it at the end minus where was it at the beginning. It's your final position minus your initial. It's not initial minus final. Displacement is a vector. The sign is meaningful. So it always has to be final minus initial. Make sure you know that. Final minus initial. All right, so now I just got to compute it. X of 3, that's going to be 9 minus 12 plus 3. I'm plugging them into my X of t. Minus X of 0 is just 3. So if you compute that, you get negative 3. Now what's the, that's my final answer. So what are the units of displacement? Feet, right? Negative 3 feet. So now it says to explain what that means. The negative means that the particle ended up at the end of 3 seconds to the left or to the right of where it started. Negative means left, okay? After 3 seconds, the particle was 3 feet left of where it started. That's how you want to write that. You always want to interpret the sign of a vector. In this case, we're not saying decreasing because it's not a rate of change. The negative just means it was to the left of where it started. Now notice that that's a lot better answer than just saying After 3 seconds, the particle was displaced negative 3 feet. What does that mean? Oh, it was to the left of where it started. I got that. Does that mean that the particle had to be moving left the entire time during those 3 seconds? No, we only took a pulse at the end and at the beginning. It could have been zigzagging back and forth anywhere in that first 3 seconds, but all we know is that it ended up at the end of 3 seconds, 3 feet to the left of where it started. Okay, sweet. Find the average velocity of the particle during the first 3 seconds. Explain its meaning. So average velocity is displacement over time. It's the net change in position over the elapsed time. So that's going to be x of 3 minus x of 0 all over what? 3 minus 0. This is, again, what we call the difference quotient. And you need to get in the habit of showing the difference quotient. How many of y'all know that 3 minus 0 is just 3? Yeah, we all do. So why would you want to write 3 minus 0 in the bottom instead of just putting 3? To show what you're doing. Yeah, you need to communicate what you're doing. And if you don't show the difference quotient, that's one of the big things that College Board and I will both be picky about. If you don't see the difference quotient, you're not going to get checked for your setup. So make sure you're showing it. Now we can plug in. We happen to have computed the displacement in part A, so I know it's going to be negative 3 over 3, which equals negative 1. Now what are the units? Yeah, feet per second, I guess, because the top is units of feet, the bottom is time, which is in seconds. So that's feet per second. And now to interpret it, what does the negative mean? Yeah, was it going left the whole time necessarily? No, it just averaged 1 unit to the left, feet per second. So you could actually say this. The particles, we know what velocity is. The particle's average velocity was 1 foot per second to the left during the first 3 seconds. And I kind of broke the mold on this one because I usually want you to start with the introductory adverbial clause that references either the moment in time or the interval of time, because you have to say that. So normally I would say during the first 3 seconds, comma, the particle's average velocity was 1 foot per second to the left. You always want to interpret a plus or a minus sign in a vector quantity in your write-up. Okay? You could also say that its position on average was decreasing by 1 foot per second. That means the same thing. All right, part C. Find the particle's initial velocity and its velocity at 3. Explain the meaning of each in terms of the particle's movement. So now it's the velocity at initial time at 3. That's the instantaneous velocity. We need the what for that? The derivative. So let's go ahead and find it. If x of t was equal to t squared minus 4t plus 3, then the derivative, we got to show it. We, at the very least, call it x prime of t. That's required. I would like for you to call it v of t then as well. It's going to be nice because then you're giving it a meaningful name. And now you take the derivative using the power rule, 2t minus 4. And now we want to know what was the initial. So what does the time correspond to for initial? 0. So I'm going to call it v of 0 now. You can't say v of 0 if you never defined it, but we did define it right here. We said v is equal to x prime. So don't just pull v out of a hat somewhere. If you didn't call it v, you would be using x prime as 0 right there. It equals negative 4 feet per second, and v of 3 was 2, if you plug it in, feet per second into the derivative. So you don't have to show those calculations because the notation on the left pretty much implies what it is you're doing. And so what does that mean? Well, I'll just say it here. At t equals 0 seconds, or initially, comma, the particle was moving what? Left at 4 feet per second, and in the end, at t equals 3 seconds, it was moving to the right by 2 feet per second. So the sign of the velocity tells you if it's moving left or right. So it wasn't going left the whole time, was it? It went left and then it went right, maybe even danced around a little bit. Find the acceleration when t equals 3. At t equals 3, that's at a single instant and moment in time, right? So that's instantaneous acceleration, not average. By the way, how would you find average acceleration? The difference quotient, right, of velocity. V of B minus V of A all over B minus A. But we want the instantaneous acceleration, so I need to find its derivative. So because I called it V up above, I can just say V prime of t, and again, I'll give it a meaningful name. I'll call it A of t, and it just ends up being 2. Does that mean I've answered it for t equals 3 since it's a constant? No. I still want to say A of 3 equals 2, and that would be feet per second or feet per second squared. Explain its meaning in terms of the particle's velocity. Okay, that's interesting. So instead of just saying at t equals 3 seconds, comma, the particle's acceleration is 2 feet per second squared, I need to get the word velocity in there. So remember, the acceleration is also the rate of change of velocity. So was the velocity increasing or decreasing? Increasing, because that's a positive number. So here's what you'll say. At t equals 3 seconds, comma, the particle's velocity was increasing. And so here's the sentence writing again. And because I'm interpreting in terms of the previous function, I'm going to say increasing by 2 feet per second each second, or per second, or a second. Right? You want to interpret it as the previous function's units per unit of the independent variable. So for every second that elapsed, it was gaining at that time another 2 feet per second in velocity units. All right? At t equals 3, is the speed of the particle increasing or decreasing? Well, we just said that the acceleration was 2, so the velocity was increasing. If the velocity is increasing, does that mean the speed has to be increasing too? Right, very good. No, that's not the case. If you have a negative velocity that's increasing, now your speed is decreasing, okay? So we have to look at what 2 things to talk about speed? Velocity and acceleration. So I need to figure out what V of 3 is, and I need to figure out what A of 3 it is. Well, A of 3 we just figured out was 2 feet per second, which was or second squared, which was a positive number. Did we ever figure out what V of 3 was? Yeah, we did up here on part C. It was 2. So V of 3 also equals 2 feet per second, which is also greater than 0. So you do have to tell me what the sign of each of them is. You can't just say they are the same sign. You have to tell me what the sign is. In this case, they're both what? They're both positive. The justification is that right there. All you have to do is show me what that number is in relation to 0. That number is greater than 0. That number is greater than 0. So, at t equals 3 seconds, comma, the speed is what? Increasing. The speed is increasing. If one had been greater than 0 and the other had been less than 0, then you would say, so at t equals 3 seconds, the speed is decreasing. So you do have to say what the sign is. Very important. You can't just say, since they're both the same sign, and not tell me what the sign is, even though that really is all you need. College Board will take off if you do not tell them what the actual sign of each is. All right, so this would happen to be one where both the velocity and the speed were increasing, but that's not always the case. At what times does the particle move to the right or to the left? What am I going to use to analyze that? It's moving to the right when its position is increasing, right? Which is when its velocity is positive. Positive velocity means moving to the right, yeah? Negative velocity means moving to the left. So let's kind of get our velocity function again. It was 2t minus 4. The velocity function was 2t minus 4. I know that that's a graph of a line, yeah? And I know it's going to have one t-intercept, and it will change signs there. It's not going to bounce off the axis. So let's go ahead and find the t-intercept by setting it equal to 0. Now, most things in the physical world, when they change directions, have to pass through a velocity of 0. They have to decelerate enough to hit 0, and then they change direction. But in the math world, you do not need things necessarily passing through 0 through a continuum in order to change signs. As long as it's negative one time and positive another, you can have problems where things jump across the x-axis. But I know 2t minus 4 is a continuous function, right? So by the IVT, when it goes from negative to positive or positive to negative, it has to pass through 0. So that's why I can set it equal to 0. So 2 equals 4, and t equals 2 seconds. All right, so now quickly, here's one way. You want to test the intervals here. You can either set up a little number line chart or just think about what the graph is going to look like. Here's 2. The slope of the line is positive, right? So it looks like this. So the velocity actually goes from negative to positive. Why is that important? You're going to have to tell me how the sign changes, okay? If you didn't want to do that, you could do a little number line. You could say, here's t, here's v, here's 2. Pick a number from the left of 2, like 1, and a number from the right of 2, like 3, and plug them into your velocity function. When you plug in a 1, you get a negative number. When you plug in a 3, you get a positive number. Okay? So here's what you would say. The particle is moving, and I'm just going to say dot, 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 and underneath there I'll put a little bullet point. Left, when is it moving left? Whenever the velocity is negative, which is what? Everything to the less than 2? Remember I told you up here that this was kind of important? When they throw something at you in the beginning, it's probably for a good reason. It means that it's going to be relevant somewhere in the problem. Here's where it's relevant. The line, the equation 2t minus 4, is negative everywhere to the left of 2. But if you just say left for t less than 2 seconds, you're not going to get full credit. You'll lose points. Okay? So here's what you have to say. For 0 less than or equal to t less than 2. Now, why do I include the 0 and not the 2? Yeah, if you look at t equals 0, the value of the velocity is, in fact, a negative number. So it starts off initially, immediately, at that instant, moving to the left. But at 2, it's 0, so it's technically not moving left at that point. And then the justification would be, since b of t is less than 0 on this interval. So we kind of gathered our evidence over there, and now we're answering it with a justification. That's so important to be able to do that. It's moving left from 0 to 2 seconds, put units, comma, since the velocity is negative on this interval. Now this is a judicious choice of a pronoun. Is there any doubt to what the antecedent to this is in this sentence? This interval clearly refers back to that one there. You don't want to get in the habit of using pronouns, though. Okay? It's kind of a dangerous thing here. And then it's moving right for what values of t? Greater than 2? Do we have an upper bound like 5 or infinity? No, we don't. So you could say for t greater than 2. Since, or seconds. Ooh, I almost lost a point. Seconds. Since v of t is greater than 0 on this interval. Very important. Okay. I feel like we're getting to know this particle pretty well. When does the particle change direction? At t equals 2. How do we know that? Just because the velocity is 0? Yeah, what's happening to the sign of velocity at 2? It's changing, right? So it really has nothing to do with 0, believe it or not. I mean, the fact that it's a continuum, you can have functions that bounce off the t-axis, right? So just because the velocity is 0 doesn't mean it changes direction. So what's important is to say the following. The particle changes directions. The particle changes directions at t equals 2 seconds, comma, since, and here's the easiest way to say it, since v of t changes from negative to positive at t equals 2 or at this point. That's another judicious use of a pronoun. Okay, you could almost say at t equals 2 seconds a little bit faster. Because there was a sign change in velocity. Thank you. To the left, it was negative, so it was moving left. And to the right, it was positive, so it was moving right. So that's where it changed. You don't even have to say since the velocity is equal to 0 at that point, because that's not necessarily going to happen in the future. If you had a piecewise function that was given to you, the velocity could actually jump from negative to positive or positive to negative without ever passing through 0. So it's because the velocity changes signs. Now, does it really matter how the velocity changes signs in order for the particle to change direction? Not really, but guess what College Board wants to see? It wants to see how it changes direction. So if you just said, since the sign of the velocity changes signs there, I might be like, okay, I'm cool, I'm with you on that. Since the velocity changed signs at t equals 2, change directions. But College Board wants to see how it changed signs. So that's why we always say how. It changed from negative to positive, not in France, but at t equals 2, at this point, which we've already mentioned in that same sentence. So for these problems, you're really learning how to present your justification to get full credit. That's what they're about, really. Okay, part G. Find the total distance the particle travels during the entire first 3 seconds. Find the total distance. How are you going to figure out the total distance it travels? We want not the net displacement. We don't want the net change in position. We want the total gross movement. If it went 3 to the right and then 3 to the left, its displacement was 0, but it traveled 6 units. That's what we want to know. Anybody know how to do that? Well, I thought I saw something up here. It says, what is it? It said something. Distance traveled is the sum of the absolute values of the distances between turning points. Oh, so that's what we need to do. Okay. How do we do that? I'll show you how to do it. Let's take a look at x of t, the position function, okay? I'll do it right here. Let me redraw it. X of t is equal to t squared minus 4t plus 3. That's a parabola that opens what? Up, down, left, or right? Or inward? Up. Okay, good. If I set it equal to 0, I can find the x-intercepts. Let's factor it. T minus 3, t minus 1. That means that t equals 1 and t equals 3 are the x-intercepts. Let's go ahead and sketch a little graph of that little dude. All right, so my first t-intercept was at 1. There was 2. There was 3. There's an x-intercept, and it opens up, y'all said, right? So it looks something like this. The midpoint of 1 and 3 is 2. That's the vertex, so I'll go ahead and draw that. Now, why did I not draw it to the left of the y-axis? Can't be less than 0. Good. So I'm measuring t over here in, I forgot what the units were, seconds. And I'm measuring its position on the x-axis, on the vertical axis here. That's x of t in feet. So now you kind of know what it's doing, right? When the slopes of this graph are negative, the velocities are negative, yeah? Now we have something to look for. Since the instantaneous velocities are the derivative of this graph, and the derivative of this graph are the slopes, wherever this graph has a negative slope, the particle's moving left. So notice now we know for sure. Remember I said we don't know if it was moving left the entire time or right the entire time? Notice that the function is monotonically decreasing from 0 to 2. That means that our particle was monotonically moving to the what? Left the entire time. I can figure out now how far it traveled in the first 2 seconds by figuring out this vertical distance. Now, what am I going to need to do that? I need to know kind of where it ended up. So I need to know x of 2 minus x of 0. And because I don't want that to be a negative number, I'll just take the absolute value of it. Plus, then I know it turned around, and now I can figure out the vertical distance that it went as it turned around and went back towards the origin. I will add to that then the position or the displacement from 2 to 3. But because I don't want it to be negative, I want to figure out the total gross movement, I'm going to take the absolute value of it. That make sense? So it traveled some distance moving down, and then it traveled some distance moving up. And I want to find out the two positive values that represent those distances, not directed distances, and add them together. And so that's how we can do it. So you have to know where it turns around, which is, the graph was helpful. All right, so now we can just do some computations. What was x of 2? Well, it's going to be 4 minus 8 plus 3 minus x of 0 was 3. So I'll take the absolute value of that one. Plus x of 3, I think we already figured out. Well, what was x of 3? We did that way up here. It was 0, right? Yeah, it's right there. Okay. 0 minus x of 2 again is going to be 4 minus 8 plus 3. So we take the absolute values. So this turns out to be a negative 1 minus 3, that's negative 4. So the negative means that it went down 4 units, right? Y'all see that? In the first 2 seconds, it had a y-intercept of something and it went down 4 units. And then it turned around and went back up. So if we add these together, that's going to be negative 1. That's 1 unit. It went back up. So we end up with 4 plus 1, which is 5 feet. So that's kind of a tedious calculation. Not bad for a parabola, because we know a parabola just turns around once. But if you had like a cubic or something and it turned around more than once, what you're trying to do essentially for distance traveled is you take your position function and you figure out the total distance vertically it travels between each turning around point, okay, between each local max and local min, and then you add together their positive quantities. You're probably not going to have to do this on one of my tests or an AP exam. When we get to particle motion part 2 later on, total distance traveled becomes a much easier thing to compute once we know how to take the antiderivative of something. But right now, I just want you to be aware of the process. It's a little bit tedious. Okay, so it traveled 5 feet. It traveled 5 feet to net how many? Negative, yeah. It netted 3 feet to the left of where it started, but it traveled 5 total feet to net 3 feet to the left. Okay, that's kind of what we said. All right, so we kind of told the story of this particle. Make a good children's book, right? The story of the particle. Not really. Any questions about the particle or the problem? I kind of hate to leave it. Let's leave it. Okay. Example 7. Instead of giving you an equation now, I'm giving you not a giraffe, but a what? A graph. Right, a graph. So we're going to have to know how to read the graph. So let's read. The graph above shows the position. All right, so it's a position function. So instead of giving you an equation for the position, it's a graph now, y of t, for a particle moving now along not a horizontal line, but a vertical line. So you can imagine like it's an inchworm or something, moving up and down or down and up along a water spout that is the y-axis. Hello, thank you. Nancy, you look like you had your feelings hurt when I gave him 2 and you none. So there's yours. For t equals 0 to 7. All right, so again, this is kind of meaningful. We're not looking to the left of 0. We're not looking to the right of 7. Everyone got it? And we're moving up and down or down and up on a water spout. Sweet. On what open interval is the particle moving down? Well, now, instead of moving left and right, we have up and down. So we're still looking at the velocity, right? When the velocity is positive, it's still moving in the positive direction, but it's not right in this case. That would be up. And when velocity is negative, we're moving in the negative direction, which is not left in this case, but rather down, down. So sometimes you could justify, notice how it says justify? You can sometimes justify ahead of answering the question, and it almost helps you answer the question. So let's do this one that way. On what intervals is the particle moving down? Well, what do I know? I know that the particle is going to be moving down when the derivative of position, which is the velocity, is less than 0. Okay, I got that. All right, so if this is the graph of y, I want to look at the derivative of this graph, which means I'm looking at the what's of this graph. the slopes. So I'm going to say that to myself. I'm going to say, okay, that's going to equal then when the slopes of y of t are less than 0. Okay? You always want to relate it to what you're given. We're given the graph of y, so you have to justify in terms of y, the graph. So now you've already told me, you've already justified. You're about to tell me where the slopes of the graph are negative, or equivalently, where the graph is decreasing. Yeah? Where is this graph decreasing? Between what time values? From 2 and 4. So you could do it like this. 2 less than t less than 4. And what? 6 less than t less than 7. And then do we have units here? Seconds. So you would put seconds on the end. So you could do it like that. That's an okay way to do it with inequalities. Or you could say for t epsilon, 2 comma 4 union 6 comma 7 seconds. I kind of prefer the interval notation in this case, but either one works. And sometimes you're given the information, you know, on a test or a quiz in interval, sometimes in inequality notation. So I'm just going to paste that down here. So have I already justified then? Did I use units on my final answer? Yeah. So again, the justification points would be right here. You've told me exactly what you're looking at, and then you've answered the question. If you hadn't done that, you would do this and say, since the slopes of y of t are negative on these intervals, or since the graph of y of t is decreasing on these intervals. But sometimes, again, justifying ahead of answering it helps you answer it. Next one, on what open intervals is the particle at rest? Lazy particle. What are we looking for now? Particles at rest when what? When the derivative is 0. The derivative of what? Of y. Yeah, when the velocity is 0. Particles at rest when it's not moving, when the velocity is 0. So that's going to be when the what's of the graph are 0. Yeah, there you go. So let's say at rest when the slopes, don't just say when the slopes are 0, because you know what I'm going to say, you know what College Board's going to say? They're going to say the slopes of what? Heavenly Ski Resort in Lake Tahoe? I wish. No. At rest when the slopes of y of t are 0. That's now communicating exactly what you're looking for. Hey, do we have 0 slopes on here? Yeah, on the open interval from who to where? 0 to 2. Okay. You could then say this occurs, if you want. This occurs for t epsilon 0, 2 seconds. Make sure you put units on your answers. So I like the interval notation better than the inequality notation. At what times does the particle change direction? Particle changes direction when the velocity changes sign. The velocity, again, are the what's of the graph? Slopes. So this is going to happen. This occurs when the slopes of y of t change signs. Now notice I just said in the previous from we have to say how the sign's changing. But for what I'm looking for, the slopes change signs. Okay, so is that going to include when it goes from 0 to negative? No, because it's not even moving there. So here this goes from a negative slope to a positive slope. So that's going to occur at what? T equals 4, and then at t equals 6. So you could say at t equals 4 seconds, comma, since the slopes of y of t change from what to what? Negative to positive. At t equals 4, you say it again, seconds. And at t equals 6 seconds, kind of the same thing, but opposite, since the slopes of y of t change from positive to negative. Not in France again, but also at t equals 6 seconds. So it almost seems redundant, but it's not. You're saying here is where it changes direction because that also happens to be the location where the signs of the slope of the graph that's given, y of t, change in this manner. Okay? Not like it changes directions here because over there it did something. You're saying here's where it happened. That's why this is where it changed directions. All right, so that's a little bit of writing, but it's cool. You're saying everything you need to, and you're getting full credit. Dun, 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 dun. So it matters how the sign changes, so you need to make sure that you always say how the sign of something changes. During the first 6 seconds, what's the particle's displacement? Well, let's go ahead and write it out here. DISP can be short for displacement. That's your net change in position. I want to know where it was on the vertical line at 6 minus where it was at 0. So there is your computational setup. And where are you supposed to get those values? From the graph. What is y of 6? 0. And what's y of 0? 6. Cool. So this is going to be 0 minus 6, which equals negative 6. And what are we measuring in the vertical? Inches? Yeah, inches. So if it did ask us to write a sentence, we would say during the first 6 seconds, the particle ended up 6 inches what? Not left this time. Below where it started. Oh, at the end of 6 seconds, the particle ended up 6 inches below where it started. So right now we're only doing linear motion. That's it. It's either going to be vertical or horizontal. Most of the time it's horizontal, truth be told. But when it's vertical, you need to make sure you're saying the right thing. 6 inches below where it started. Okay. During the first 6 seconds, how many inches does the particle travel? Well, this should be a little bit easier now because we don't have to generate the graph. We actually have the graph. But it's the same idea. It moves downward by some amount, and then it moves back upward by some amount. So the distance traveled is going to equal what? Well, this one's a lot easier to compute, right? We don't actually have to plug in numbers into an equation. We can just look at the y values here. How far does something travel when it goes from positive 6 to negative 6? 12 units. Plus, how far does it go from... Oh, sorry. We're going to put this on the recording. And to the republic for which it stands, one nation, under God, indivisible, liberty and justice for all. We're standing. I pledge allegiance to thee, Texas, one state under God, one and indivisible. Okay, moment of silence I'm going to cut in. I'll give you an extra moment of silence at the end. It went 12 going down, and how far did it go going back up, back to the origin? 6. So 12 plus 6 was 18 inches it traveled. Okay, there you go. That was the total distance traveled. And now a moment of silence. All right, that's good. We're going to keep going. I'm going to finish this problem during the announcement. So if they come on there and talk, listen to me, not him. What is the particle's velocity at 5 seconds? Velocity at 5. Well, velocity is the derivative of this, right? So we're looking for the what on this graph? The slope, right? So here we go. I want to know what is the slope? What is the slope of y of t at t equals 5 seconds? All right, so now I have something to look for, right? I go up to the graph, the t equals 5, and hey, luckily it's on a line segment, so I can compute the slope, yeah? What's the slope? Well, it's the change in the y, which how far was it from negative 6 to 0? It was 6 units. Over the change in the x from 4 to 6 was how far? 2. And it was a positive slope, so just check that, right? It's going up, so it's a positive number. So it should be what? 3, and then the units would be inches per second. So let me cut that and put it down here. Paste. So it says explain what this means in terms of the particle's movement. We'll just say, you can actually call this, if you want now, you can call that y prime of 5. That's kind of nice too. That puts it in a calculus form instead of just m for slope. I'm going to say it, not write it, because I don't think we have time. At t equals 5 seconds, comma, the particle was, or the particle's position was whating? Increasing. Or you could say the particle was moving what? Up. Yeah. At t equals 5 seconds, the particle was moving up at 3 inches per second. Or its position was increasing. Usually when you're talking about particle motion, you do want to say left or right, up or down, instead of position increasing, position decreasing. It's just a little bit better. So at t equals 5 seconds, the particle is moving up at 3 inches per second. What was the particle's velocity at t equals 5.999? Well, 5.999 is on the same line segment, right? So it's the same. So y prime of 5.9999 is equal to 3 inches per second. What is the velocity at 6 seconds? Is it considered 0 or D and E? True. One of those. Which one? You can't think of what actually is going to happen. If something's going to turn around, it's going to pass through 0. But that's the sharp turn. And the derivative is what we're looking for here, and the derivative doesn't exist there. So it is D and E. It is D and E. So this is like a subatomic particle that's breaking the law of physics, okay? And that's fine. Let the math tell the story. Don't you tell the story. Y prime of 6 equals D and E. There's a sharp turn there. The slope from the left is not equal to the slope from the right. During which time intervals is the speed the greatest? If we're looking at speed, that's the absolute value of velocity, right? Which is the absolute value of y prime of t. So I want to know then when the slopes have the greatest magnitude. Not just when is it the most positive, but where is it the biggest magnitude? Where is this graph the steepest? Yeah, from 2 to 4. Even though it's negative, from 4 to 6 is not as steep as it is from 2 to 4. And we're looking at absolute values. So the speed is the greatest from t equals 2 to 4 seconds. I'll write it like that. And where is the velocity the greatest? Well, now we want the greatest slope, not magnitude. And unfortunately, as steep as that one was from 2 to 4, it was a negative number if we don't take the absolute value of it. And so even the smallest positive slope is going to be greatest than the steepest negative slope. So where is this slope the most positive? From 4 to 6, yeah. And that's the difference between, vector quantities and scalar quantities. And then the last part here, and we'll call it a day. What's the particle's acceleration at t equals 3? At t equals 3, that's right here. What are we looking for on that? The change in the slope of the graph of y of t. Excellent. There you go. We want to know how we want to look for the change in the slope of the graph of y of t. That's relating essentially the second derivative to our graph. And so what can you tell me about how fast the slope is changing right there at t equals 3? It's not changing, right? Because it's part of a line segment and lines have constant slopes, that line's slope is not changing, and therefore we could actually say y double prime of t, or let's do 3, y double prime of 3 equals a of 3, if you want to call it. Now you've defined the acceleration function, is 0 feet per second squared. And it didn't say to justify. Usually a question like that, they're not going to ask you to justify. But we would know exactly what to say because the slope of the graph does not change at t equals 3. It's part of a line segment. Okay? So there you go. That was one particle motion question from the graph, one from the equation. In both cases, we had the position function given to us. Tomorrow we'll look to see how we answer questions when the velocity equation or graph is given to us. And it's a pretty robust section. We're on page 7 and 9, so we might finish tomorrow. I'm hoping to. Actually, That won't happen. I'll tell you why here in a second. Your worksheet's going to be due on Tuesday. Okay? Worksheet's going to be due